Now the next problem is, two conductors have the same resistance at 0 degree centigrade, but their temperature coefficients of resistance are alpha 1 and alpha 2. The respective temperature coefficients of their series and parallel combinations are nearly. That means at T equal to 0 degree centigrade, the resistance, let us say, is R0 for both the resistors. Okay. Now, when you increase the temperature to T, okay, at that time their resistance would be R0 1 plus alpha 1 T, and for the second it will be R0 1 plus alpha 2 T. Okay, now let us take the first case of series combination. So when both of them, they are connected in series, okay, let us say this is R1 and this is R2, so their R series would be equal to R1 plus R2, which in turn can be written as R0 1 plus alpha 1 T plus R0 1 plus alpha 2 T, which in turn can be written as 2 R0 plus R0 alpha 1 T plus R0 alpha 2 T, which can be further written into as 2 R0 common 1 plus alpha 1 plus alpha 2 by 2 times T. Now this R series, if they were connected at T equal to 0, then their effective resistance would have been 2 R0. R0 plus R0 is 2 R0. So here you can see that 2 R0 1 plus alpha series T is equal to 2 R0 1 plus alpha 1 plus alpha 2 divided by 2 times T. Okay, now if you solve this, you will get alpha S as equal to alpha 1 plus alpha 2 by 2. Okay, now let us do it for the parallel combination. So when you connect them in parallel, this is R1, this is R2. Okay, so resistance in parallel is given by 1 upon Rp is equal to 1 upon R1 plus 1 upon R2. Also at T equal to 0 degree centigrade, R1 R2 is equal to R0, therefore resistance in parallel at 0 degree centigrade would have been 2 upon R0. Okay, or Rp is equal to R0 by 2. But if you increase the temperature, then the resistance would be different, and in that case the effective resistance in parallel would be 1 upon R0 1 plus alpha 1 T plus 1 upon R0 1 plus alpha 2 T. Okay, now from this you can take 1 upon R0 as common, and this expression 1 upon 1 plus alpha 1 T by applying the binomial theorem could be written as 1 minus alpha 1 T and 1 minus alpha 2 T. Okay, which is equal to 1 upon R0 2 minus alpha 1 plus alpha 2 by 2 times T. Okay, now you can take 2 common. Now this will become 2 by R0 1 minus alpha 1 plus alpha 2 by 2 times T. Now on the LHS side, 1 upon Rp can be written as 1 upon R naught by 2, 1 plus alpha p T, where alpha p is the coefficient of resistance, temperature coefficient of resistance in parallel combination. Now you can write this as 2 upon R naught, and the term 1 upon 1 plus alpha pt applying binomial theorem could be written as 1 minus alpha p into t. Now you compare this equation with this. So this will cancel out, then 1 will cancel out, and you will get alpha p as equal to alpha 1 plus alpha 2 divided by 2. So when the initial resistance is same, okay, so whether you connect them in series or whether you connect them in parallel, you are going to get the same temperature coefficient of resistance. Okay,